All right, let's dive right in. Today, we're going to take a journey deep inside our own nervous system to uncover the incredible story of how our brain cells actually talk to each other. So here's the game plan. We're going to follow the path of a single neural signal, starting with the messenger cell itself. Then we'll look at the spark that creates the signal, the incredible leap it takes between cells, the chemical keys that unlock the message, and finally, we'll see what happens when this absolutely vital communication line breaks down. Okay, first things first. Let's meet the absolute star of this entire show, the fundamental building block of our whole nervous system. So this right here, this is a neuron. Specifically, it's the most common type you'll find in your central nervous system, your brain and spinal cord. It's a highly specialized cell, and its whole job is to send information using this amazing combination of electrical and chemical signals. The best way to think about it is like this. It's kind of like a tiny biological wire, but it's also got its own little processor built right in. It receives signals through its dendrites, processes them, and then sends messages out through its axon at unbelievable speeds. Okay, so we've met the neuron, but how does it decide to, fire? What's the trigger that takes it from just sitting there to blasting out a critical message? Let's get into it. You see, a neuron is getting bombarded with little signals all the time, but it can't react to everything, right? It has to have a way to decide which messages are actually important enough to pass along. And this is where it gets really cool. It all comes down to two kinds of signals. You've got graded potentials, which are like little localized whispers. They're small and they fade out pretty fast. But, and this is the key, if you get enough of these whispers adding up at the same time, they can hit a critical threshold. And when they do, they trigger an action potential. That's the all or nothing shout that travels the entire length of the neuron without losing any of its power. All right, so our all or nothing shout, that action potential, has raced all the way down the axon. But then it hits a roadblock, a literal gap. So what now? How in the world does the message make that leap? And the answer is right here. This is a synapse. This is the place where the magic happens, where that electrical signal has to completely change its form to get across. See, that electrical spark, it can't just jump across the gap. It's not going to happen. So instead, the neurons is something incredible. It converts that electrical message into a chemical one by releasing these special molecules called neurotransmitters. And this right here is the absolute heart of neurotransmission. You've got an electrical signal coming in that triggers a release of chemicals. Those chemicals float across the gap, latch onto the next neuron, and boom, a brand new electrical signal starts up. It's this incredible, elegant conversion from electrical to chemical and right back again. So let's talk about these chemical messengers. I mean, who are these things? Well, it turns out they are the keys that unlock basically everything we do, from moving a muscle to feeling our deepest emotions. And it's not a one-size-fits-all kind of situation. Not at all. Each neurotransmitter has a very specific job, acting kind of like a unique key that will only fit into certain locks, or what we call receptors, on that next cell. And you really can't overstate how delicate this chemical balance is. I mean, just look at Parkinson's disease. What you're seeing here is what happens when the cells that produce dopamine start to die off. A deficit in just one of these chemical keys can have these absolutely profound, devastating effects on the body's ability to control its own movement. This communication network is unbelievably resilient. But what happens when the physical system that it relies on, when that breaks down catastrophically? Well, one of the most devastating examples is a stroke. This is just a brutal breakdown of the brain's whole support system. It essentially starves the neurons of the oxygen they need to function, to communicate, and without that oxygen, they start to die. And there are a couple ways this can happen. Ischemic strokes, which you see on the left, are caused by a blockage, like a clot. They're actually the most common. But then you have hemorrhagic strokes on the right, and that's where an artery actually ruptures. These can be even more dangerous because you have blood leaking out and directly damaging that delicate brain tissue. Now, let's shift gears a bit and think about the spinal cord. If the brain is the command center, the spinal cord is the main information superhighway connecting it to the entire body. And if you damage that highway, well, you sever those lines of communication, and the results can be incredibly and devastatingly precise. And it really boils down to a pretty simple but critical rule. The higher up the injury is on the spinal cord, the more communication lines get cut. It's that straightforward. And that directly explains why an injury to your neck, the cervical region, is almost always far more severe than one in your lower back. So, when you step back and look at the whole thing, from that tiny little change in voltage to the grand symphony of our thoughts and feelings, it's all just this incredibly intricate dance of electrical sparks and chemical messengers. And that really leaves you with a pretty staggering thought, doesn't it? Our entire conscious experience, everything we think and feel and do, is built on this very physical, very biological process. And the most mind-bending part? This elegant biological machine, the brain, is the very same tool we're using right now to try